Thank you for attending this presentation. Today I would like to present our paper on Riemannian Manifold Learning for Robot Motion Skills, which combines different aspects of motion skills representation from a geometrical perspective. First, I would like to talk about why we should consider the manifold geometry learning, specifically Riemannian manifold, in order to do learning for motion skills. The most important reason that made us think about using geometry is the amount of information that can be gained by capturing the geometry of the data. And this information can be used to facilitate the learning process or even generalization in learning a complicated task. Obviously, there are several restrictions in capturing the geometry, like the high dimensionality of the ambient space. Therefore, we have to make some assumptions. The data does not cover the whole ambient space, so the data is sparsely distributed. The data lies on a manifold in a low-dimensional latent space, and the manifold is a Riemannian manifold. How do we actually capture this geometry? Different people might have a different interpretation of the geometry of the data, and sometimes the word might be a little bit misleading. In our work, when we mention geometry, we mean the uncertainty. The uncertainty might simply means the area with more data has lower uncertainty and other way around. So without uncertainty, there is no geometry. Imagine having the latent space with latent data representation as this image. Now we can see the areas with low uncertainty show where the demonstrations have happened. And we can use this information to our favor to produce more similar motions, which we will talk about in a minute. First of all, the Riemannian manifold are described by Riemannian metric tensor, which is actually the collection of a smoothly varying inner product defined on the tangent space of the manifold. And we define it like the M tensor that you can see in the slide, which we also call it the pullback metric. So to deal with our assumptions regarding Riemannian geometry, we need two important components: the latent representation Z and a probabilistic mapping between the latent space and the ambient space to calculate the pullback metric from the tangent space. These two assumptions are guiding us to use generative models, and specifically variational autoencoder, which is a close fit to our assumptions, as you can see. Now, having learned the necessary components for our manifold, we can think about using geodesic to reproduce motions. The geodesics are shortest paths on the manifold between 2 points, and they are the equivalent of straight lines in the Euclidean space. In this case, that the latent codes are actually the encoded motion trajectories from circular motion demonstration. Following the geodesic can give us a motion similar to circular motion that has been demonstrated, that is somehow generalized and inherent to the learned manifold. The length, as you can see, is defined based on our stochastic function and eventually related to our metric tensor. By minimizing, we achieve a local geodesic, as you can see in the plot. The right plot shows how the variance, uncertainty, or manifold looks like in the latent space. And in this picture, you can see a different manifold training using demonstration, which are the positions of the end effector and being used to generate geodesics that represent similar motions as the demonstrations. The way of representation of the length gives us the flexibility to add more constraint without training the network again. We can add abilities like obstacle avoidance on the fly for the new geodesic. If we define the length as below, you can see in the result the geodesic that considers the obstacle as blue curves that successfully avoided them, and the green ones, which are the simple geodesics, they did not. For our future work, we consider including dynamic obstacles and also the orientation of the end effector. Thank you for your attention. I would be happy to answer your questions now.